Hello everybody. In this video we'll be talking about AP Chemistry's topic 6.2, energy diagrams. So with energy diagrams, this is just a visual way of representing the energy that's lost or gained in a chemical reaction, as well as the energy that's lost or gained that's needed in order for the chemical reaction to take place. So we're going to look at two different types of reactions. We're going to look at exothermic and endothermic reactions and see how energy diagrams relate to those two different processes. So let's first start with an exothermic reaction. I'm using the rainbow pen. I don't use it very often. My wife said that it's silly, but personally, I like the rainbow pen, so I'm going to use it. Anyway, so this is an exothermic reaction. So what happens in an exothermic reaction? What does exo mean? Well, exo means to leave, and so energy leaves the reaction. So an energy diagram puts on the x-axis the reaction progress. In other words, how the progress. Talking and writing. Reaction progress. So how the reaction progresses from reactants to products. On the left-hand side, we're going to put the energy at a particular moment along that reaction progress. So initially, you have reactants. And so reactants are going to start at some plateau before they react. In other words, how much energy is stored in those bonds. And you could actually have numbers on this that tell you quantitatively how much energy there is. I'm not going to do that. I'm going to keep this qualitative. But you could have numbers on there and figure this out. So how much energy is stored in the bonds of the reactants? Those bonds have to be broken in order for the reaction to take place. And so on the energy diagram, you're going to see this hump, which represents the amount of energy necessary to break the bonds in our initial reactants so that they can actually react with one another and form products. We'll talk more about that in just a second. Then, after you've broken those bonds, those substances can now react with one another. And in an exothermic reaction, the products are going to have less energy stored in the bonds than the original reactants. So let's look at the different parts of this graph. These are our reactants, always on the left side of the graph. It's how much energy the reactants have stored. When they react, it's going to take a certain amount of energy to break the bonds in those reactants. The energy from the reactants energy to the top of this hump is called the activation energy, and we abbreviate that E with a little subscript A. So activation energy. Up at the top there, you have what's called a activated complex or transition substances. So activated complex. These are substances that are ready to react. And now once you've gotten to those activated complex, they can bump into each other and make your new products. And we'll end up with our products, which are always going to be on the right side of the graph. Now notice energy went from reactants down to the products. So if we extend this line for our products, this difference is the amount of energy that was lost in this reaction. This is called the enthalpy of reaction. It was the energy that was lost in the reaction. Notice it's downward. The products are lower than the reactants. So in an exothermic reaction, your enthalpy of reaction is negative. So energy was lost. So we have our reactants up here, products down here, reaction progress, took energy to make this reaction occur. So that is our exothermic energy diagram. Just a note, this hump determines the kinetics of the reaction. In other words, how fast the reaction occurs. The bigger that hump, the harder it is for that reaction to occur, the slower the reaction. Also, just a reminder, with catalysts will lower this activation energy. And so that dotted line right there represents the activation energy with a catalyst. I know that's later, but I just wanted to remind you what that would look like on an energy diagram. Okay, so let's get rid of that because that's not what we're talking about right now. Well, that was harder to get rid of than I thought. Okay, so now let's talk about an endothermic reaction. What's an endothermic reaction going to look like? So endothermic Endo means going in, so heat going into your reaction. So this one is going to absorb energy. So our coordinate's going to be exactly the same. We have our reaction progress down here, sometimes called the reaction coordinate. Over here on the left axis, on the y-axis, we have energy. And so for an endothermic reaction, our reactants are going to have low energy, not a lot of energy stored in their bonds. Then, as the reaction takes place, it's going to have to absorb energy to get over that hump, which is still the activation energy, and our products are going to have higher energy than the reactants. So products will be up higher, reactants are lower. So now we can still label the same things on this reaction diagram. So from the reactants to the products, that is our delta H for the reaction. That's our enthalpy of the reaction. And this is going to be positive because we went from a low energy to a high energy. The energy high minus energy low gives us a positive. So delta H reaction is going to be positive. From the energy of the reactants all the way up to the very top of the hump is our activation energy, where our activated complex is. And so these are our labels on our endothermic reaction. Notice the energy went up. And so this is a reaction diagram for an endothermic process. If you have any questions about any of this, let me know. There's definitely a lot more to it, but those are covered in other videos. Good luck.